Today, we'll use MDX software to design an I-plate steel girder bridge. And this bridge is a simple span bridge, and span length is 120 feet. And based on this span length, we should be able to figure out what is the minimum depth of the girder based on the span to depth ratio. Okay, so let's take a look at the superstructure depth requirement for the steel girder bridge. And the steel girder bridge right here, we have the overall depth of composite I-beam, which include both the steel section and the concrete deck thickness. So we have the steel section plus deck thickness equals to 0.040 times span length. And also for the depth of I-beam portion of composite I-beam, which is just steel I-plate girder depth, must be no less than 0.033 times the span length. Okay, based on these two requirements, and we can calculate the minimum depth of the girder. And here we have the minimum depth of steel portion, which is 0.033 times span length. So we have 0.033 times 120 feet and get 3.96 feet. And we also have the depth of steel portion plus the concrete deck thickness, and the minimum depth is 0.040 times span length. So we have 0.040 times 120 feet and equals to 4.8 feet equals to 58 inches. And just based on that, we can start with some trial section size. So we assume that the concrete deck equals to 8 inches. So we get the D minimum depths need to be 50 inches. And based on that, 50 inches, we want to try, okay, so I have a starting point. I will try the D, which is the web thickness part. Okay, the web thickness part, web depth part equals to D, which is 50 inches, and assume that TF, which is the flange thickness, equals to 1 inch. So I have D, which is steel section, the steel section depth, including both flanges, and the web, need to be greater than 50 inches. So I have, if I try the web depth equals to 50 inches, means that the total depth of the girder will be 50 plus 1 plus 1. So I assume that the flange thickness equals to 1 and get a rough depth of the steel girder is 52, which meets the requirement of depth to span ratio. And after that, I check the total composite section, which is D plus the T. T is the concrete deck thickness. So we get D plus T equals to 60 inches, which meets the requirement of 58. So both steel section D and composite section D plus T meet the requirement of depth to span ratio. So based on that, we can assume, okay, have a size to start. So we have this depth equals to 50 inches of the web, and the total depth approximately equals to 52. And the total section, composite section, approximately 60 inches. So also based on the depth of the girder, and we can start to have some flange dimension to start with. And web thickness TW based on the local buckling requirement, and the ratio D over TW, the width to thickness ratio of the web, no greater than 150. So based on that requirement, and we can roughly estimate the thickness of the web. So we have the thickness of the web greater than D over 150, and if we use D equals to 50 inches, that's the starting point, okay? And the minimum thickness of the web will be 50 over 150, and we get 0.33 inches. So round up to the nearest eighth of inch. So we get 3/8 of inch. That's the minimum thickness of the web. And usually the web thickness is half inch to 1 inch thick. So this is a typical range of the web thickness. So we will try, okay, so we will try, since the minimum is 3/8, we will try 1/2 inch, and this is the starting point. If we design the girder and fail in shear, and we need to increase the thickness of the web, but we will use a number, and this number usually start with 1/2 inch, the minimum, and check the shear strength. If the shear strength pass, means that this thickness works, and if shear strength fails, and we have to increase the web thickness by 1/8 of inch. Okay. So after we get, so now based on the depth to span ratio, we have the depth of the web. Then based on the local buckling requirement, we get TW. Then the remaining will be the flanges dimension. So we need to have a flange width and a flange thickness to start with, and check the bending strength. If bending strength pass, means that our flange design is good, but if the bending strength failed, means that we have to increase the size of the flanges. Okay, and based on the requirement, the geometric requirement of the flange, and first we need to set the flange thickness, and flange thickness need to be thicker, 10% thicker than the web thickness. So if you already have the web thickness, we start from there and times 1.1, and that's the minimum thickness of the flange. So if we try the web thickness 1/2 inch, and we can get the TF, which is the flange thickness, equals to 1.1 times 1/2 inch, so 0.55. So round up to the nearest 1/8 of inch, that's 5/8 of inch. And usually the thickness of the flanges no less than 3/4 inch. That's the minimum. And the typical flange thickness is ranging from 3/4 inch to 2.5 inch, in this range, and those the typical thickness of the flanges. Okay. So from there, I would say that I will try start TF equals to 1 inch as a start. Okay. And after you get TF, and we have to take a look at the flange width requirement, and flange width need to be greater than the web depth over 6. So based on this requirement, we will get the minimum flange width. And if we try 50 inches for the web depth, and we use 50 divided by 6, get 8.33 inches, and means that for this bridge, if I use 50 inches web depth, and the minimum flange width need to be at least 8.5 inch. And this gives you the minimum. And the next step is determine the maximum flange width. And maximum flange width is determined by the width to thickness ratio. And width to thickness ratio need to prevent the local buckling of the flange. So the ratio is BF over 2TF, and this width to thickness ratio of the flange no greater than 12. And in order to meet this requirement, we figure out that the width of the flange no greater than 24 times TF. So for example, if your the thickness of the flange is 1 inch, means that the width of the flange cannot be wider than 24 times 1 inch equals 24. So based on the first step and the fifth step, and this give you the range of flange width. And if we try the thickness of the flange equals to 1 inch, means that the flange width need to be between 8.5 and 24. So that's give you the range of the flanges. And based on that, I have a size to start with. A size to start with. So for this 120 feet simple span I-plate steel girder bridge, based on the requirement like depth to span ratio and also some geometric requirement of the flange and width based on the width to thickness ratio. And I have a trial size to start with. And I use this size to start, and then based on the rating ratio, and if I find the shear doesn't work, I will increase the web thickness. And if I find the bending doesn't work, I will increase the size, either the width or thickness. I will increase the thickness first of the flange. If it already exceeds 2.5 inch, I will increase the width of the flanges. So for the I-plate steel girder bridge, the web provides shear resistance, and flange top and bottom flange provide bending resistance. If bending fails, and we will increase the size of the flange, and if shear fails, we need to increase the size of the web, and usually the depth of the web is determined by the deflection, which contribute to the moment of inertia. And if shear doesn't work, we do not change the depth first. Instead, we'll increase the thickness first. And if the thickness already reached the 1 inch limit, and then we can increase the depth of the web in order to increase the shear strength. Okay, so now I have a size to start like 12 by 1 for the top flange, and the web is 50 times a half, and bottom flange is 14 by 1.5. And for I-plate steel girder bridge, usually the bottom flange is bigger than the top flange. So to start, you always try a bigger bottom flange than the top flange, because for the section, I-plate girder is a composite girder, and the top flange is composite with the concrete deck. So because of the top flange and concrete deck make a composite section and usually subject to compression, then we need to make this tension flange, which is the bottom flange, bigger in order to balance the compression force above neutral axis. Okay. Steel girder bridge are all composite section. The top flange has the shear stud and make its composite with the concrete deck. So the bottom flange usually is bigger than the top flange because the top flange composite with the concrete deck, and both will provide the compression above the neutral axis. Okay, and then let's take a look at the remaining things for the description of the problem. And based on span length, we can roughly determine the size of the girder and as a starting point. Okay. And bridge was 87 feet. And according to that, we need to determine the framing. And this problem already gave us the framing, gave us 10 girder lines at 9-foot spacing. So based on that, we already know the girder spacing is 9 foot, and also the overhang is 3 feet. Based on the width 87 feet, and we can calculate the number of design lanes. And since the barrier each side is 1.5 feet wide, and we can get clear roadway equals to 87 minus 1.5 times 2 and get 84 feet. So number of design lanes equals to 84 divided by 12, so get 7 lanes. Okay. Then the next one is maximum shipping length equals to 70, and based on this one, we know that it's not possible that we only make one piece for this bridge, which is 120 feet, and we have to cut the girder into pieces in order to make the shipping work. Okay, making shipping work, the maximum shipping length is only 70 feet, and we have to cut the girder into pieces in order to make the shipping length work. And after we cut the girder, and we can field splice each segment by bolted connection in the field like this. And this shows the field splices using bolted connection, and based on each piece, and we will determine how many bolts required for that splice location. And that splice has the bolted connection on top and bottom flange as well as on the web. So this field splice make the girder continuous. Okay, and for the splice location, we need to determine the splice location at the minimum moment location under a uniform dead load. And in order to determine the splice location, we need to combine the shipping length requirement as well as the minimum moment location. And how to determine the minimum moment location? And usually we apply a uniform dead load. We apply a uniform dead load, and put this into a structural model, and you can either do this by hand or use a structural analysis software, for example, STAT, and you can just put this beam model into STAT and put the span length and apply a uniform dead load and take a look at the moment diagram. And based on moment diagram and combined with the shipping length requirement, we need to determine where is the location that has the minimum moment requirement. And this location we use as a splice location in order to minimize the number of bolts required for this location. Okay, for simple span, it's pretty straightforward, and we will decide the splice location as close as possible to the abutment or the support, because at support the moment equal to 0 and increase and get the maximum in the middle of the girder, in the middle of the span. So if the splice location close to the support means the moment value is relatively small. So based on this requirement, and we can set the shipping length 70 feet in the middle section, and then take 25 each side. So we'll use 120 feet minus 70 divided by 2, and we get 25 each side. Then this is our splice location. And if it's a 2-span bridge, what we will do is, again, we will set the support based on span length, and then we apply a uniform load on the 2-span bridge and take a look at the moment diagram, and in order to identify, okay, so now we can identify the location based on the 0 moment location, and we can determine roughly the splice location. Again, this splice location also need to consider combined maximum shipping length. Okay. Similarly, for the 3-span bridge, and we put the support, which is abutment and pier location there, and then apply a uniform load, and then take a look at the moment diagram. And again, we will have those moment equals to 0 location based on the uniform load, and then based on those locations and combined with maximum shipping length, and we can determine the ideal splice location. Okay, and for this one, 120-foot span, and we have the first splice at 25 feet and second splice at 95 feet. Okay. That's how we determine the splice location. So 3 segments, 2 splices, and first segment is 25 feet, second is 70, and third is 25. Okay. And then cross frame, and cross frame spacing is 20 feet, and the cross frame usage in order is to reduce the embraced length of the girder. And usually the bridge girder is pretty long, and in order to reduce the embraced girder, and we want to use the cross frame in order to provide the lateral torsional buckling. And here, those truss type of structure is called cross frame and provide some lateral support of the long girder. Okay, and usually the spacing is between 20 and 25. So in this bridge, we use 20-foot spacing for those cross frames, And then we can do this location for cross frame is 0, 20, 40, 60, 80, and 100, and 100, 120. And based on the location, the 0 feet and 120 feet are at abutment. So we can also call this the bearing cross frame. The location is at the abutment. Then the remaining 5 from 20 to 100, is called intermediate cross frame. So total intermediate cross frame is 5. So we have location 20, 40, 60, 80, and 100. Those called intermediate cross frame. And deck thickness is 8 inches, and deck overlay, which is the wearing surface, 36 pounds per square foot, and utility, 5 pounds per square foot, is also part of the wearing surface. So we just add them together, get 41 pounds per square foot. And the steel deck form is 8 pounds per square foot, and this is the non-composite. We treat steel deck form as a non-composite dead load. Then we have the median, 4 feet wide and 9 inches thick, and this is a composite dead load. Concrete barrier, also composite dead load, is 450 pounds per linear foot each side, and times 2 sides. Get a total barrier weight. And the live load, we consider HL 93 live load as well as New York DOT permit truck. Okay, so the configuration of the permit truck is right here. And we can find the axle load and axle spacing. And for New York DOT permit truck, we have 11 axles, and the axle load and magnitude and spacing are listed in this figure. Okay. And the material for the girder is ASTM M270 grade 50 steel, and cross frame material is ASTM A36. And usually the cross frame material, cross frame use angle or channel. Those material are all ASTM 836. Okay. So the cross frame, so this is the plan for a typical cross frame. Is like truss type of structure, and usually use the angle or the channel for the member size. Okay, so for example, this bridge use the angle 6 by 6 by 1/2. Okay, right here. Okay, so according to the description of this bridge, okay, and we did the load calculation. So right, and we have the trail size, and based on the splice location, and we can change the flange thickness. Okay? And usually at the splice location give us chance to get more economical design. And usually the middle part has a larger size, and the two side has a smaller size, because the moment in the middle is the maximum value, and the moment at the two sides is smaller than the moment in the middle. Okay, so we will try. Okay, so we will try if we use the minimum flange thickness 1 inch. Then we will try the middle portion as 1.5, and it's at the starting point. And if we find this design over-designed, like after you get the maximum performance ratio, for example, is only 0.5, means that you over-designed your flange and you need to make the thickness thinner. And if you have the performance ratio greater than 1 in MDX software, means that represents structural failure, and you have to increase the thickness or increase the width of the flange in order to make it work. Okay, and for the web, the typical I-plate girder bridge has the same web design along the entire bridge girder. So although we have a different splice sections, but we want to keep the web design same. So for the entire girder, we have the same web design, but we do have opportunity to change the flange thickness and width in order to make our design more economical. So just remember, when you design a girder, and we always keep the web design the same along the entire girder, and at the splice we will change the flange design, and usually for simple span we have the middle part has the maximum size of the flange, and the two sides, because they're subject to a lower moment, and we'll use a smaller flange size in order to make our design more economical. Okay. And the live load deflection for the steel girder bridge is span length over 800. So based on the span length that we have is 120 foot, and we times 12 inches per foot and divided by 800, and we end up get the live load deflection limit equals to 1.8 inches, means that we'll use to check the live load deflection. And for this bridge design, we need to make sure that the live load deflection no greater than 1.8 inch. If you find the live load deflection greater than 1.8 inch, means that we have to increase the moment of inertia, and usually we need to increase the depth of the web. Okay, so if the deflection doesn't work, and we will fix the design by increasing the depth of the web. Just make the girder deeper in order to increase the moment of inertia. Okay, so another thing to explain is the bearing stiffener. And bearing stiffener, and usually is at the girder end over the abutment, and that's the place to attach the cross frame at abutment. And usually is a place to put the erection, just put the erection hook. Okay, so the bearing stiffener at the girder end, and usually is the place that we do the jacking point during the erection. So I want you to take a look at the stiffener. Right here, okay? So usually at the bearing, the stiffener is called bearing and jacking stiffener. Okay, so this stiffener, the size is 1.5 inch times 7.5 inch, and this is the typical bearing stiffener size, and the width is 7.5. Okay, and the width is 7.5, and thickness is 1.5 inch, and Intermediate stiffener size have the same width, 7.5 inch, but thickness thinner is 0.5 inch. Okay, so right here. The intermediate stiffener has 7.5 inch wide and 0.5 inch thick. And this stiffener actually is the place to connect the cross frame. So the intermediate stiffener location exactly same as intermediate cross frame. So it's the same location as intermediate cross frame because we need to have the bolted connection or webbed connection to connect the cross frame to the girder. So in order to do that, this intermediate stiffener provide like a gusset plate for the connection. So that's why the intermediate stiffener and cross frame need to have the same spacing, have the same location. And this stiffener used as a gusset plate to connect the cross frame to the steel girder. And the cross frame usually is a truss type of structure like this, okay? And for the size of each member and angle is the most popular option for the cross frame member because it's light. Also, the angle is the least expensive piece in the structural steel and easy to make the connections. Okay, so that's cross frame. Usually it's a truss type of structure, and the most popular member type is the angle. And before we use the MDX, I provide some load calculations. Okay, so just put right here, and I will show you the details where we input the load, non-composite and composite load, and DW in the software, in the MDX software. Okay, so I did some calculations and put into this document, and I will explain more when we use the MDX to input the load. Okay, so now we have a trial size. We have a size to start, and we start from there and use MDX to rate this girder design. If the rating is in a reasonable range, say is from 0.7, the maximum performance ratio is like from 0.7 to 0.99, that range means that the girder design is reasonable. But if it's significantly lower than 1, like you only get 0.5, means you over design. If the performance ratio greater than 1, means that the design, the strength doesn't meet the requirement, and you have to increase based on shear strength or bending strength. Shear strength, you need to increase the thickness of the web, and bending strength, you need to increase the size. Usually we try the thickness first, increase the thickness of the flange first, and then we can increase the width as well in order to make the flange bigger to meet the bending requirement. And if the deflection doesn't work, and we need to increase the depth of the girder, depth of the web in order to increase the moment of inertia. Okay. So let's use the software, and this is the MDX software. And after you open the software, first thing you need to do is go to the file, okay, and we will do a new project. And for this new project, Okay, and first select the folder. I will use this 100-foot steel girder, this folder, and then put the name 100-foot I-plate girder. Okay, and click open, and then this window pop up. Okay, so there's 4 options: girder system rating, girder system design, line girder rating, and line girder design. So I will explain each one, and we will use this system rating, girder system rating, and this will rate all those girders, including every girder lines, like exterior girder, interior girder, every girder lines will give you the maximum performance ratio. And girder system design, and this usually know that you want the program and design the girder, and this sounds like it's pretty good to give you some dimensions of the top bottom flange and web size, but in the real world design, we don't use this option because the software is not that smart, and usually the design is super messy and it's generate unnecessary work. Okay, so this auto design option is not good, and usually the design is not very it's not the most economical option, as well as they provide too many flange sizes and the web sizes and so on, and this design is not the optimized design. So usually we do not use this for design. Instead, we use the rating option, and by doing the rating option, we will give a preliminary size of the girder to start with. So you will put some girder size, like what's the trial size of your design, like what we did. Okay, so just now I didn't share the MDX interface, so now I just share this MDX software interface. Okay, so then I will repeat this part. Okay, after you open the software, and the first thing you need to do is go to the file. And for this one, we will do a new project. And for after you open this new project, you need to select a folder. And for this one, I use 100-foot steel girder option, and the file name I just called 100-foot steel girder. Okay, so I just called 100-foot steel girder and do open. Okay, so just 100-foot I-plate girder. Okay, so after that, this window pop up and give you 4 options. And one is called steel girder rating, and second one is called steel system design, and the third one is line girder rating, and first one is line girder design. And we will use the girder system rating, and these options give you the ratings for every girder lines in this bridge, including both exterior girder and interior girder. And every girder lines, for example, you have 10 girder lines in this example, and this gives you the maximum performance ratio for all 10 girders. And the second option is the system design. Is actually you just input the loading and so on, and this program will give you some automatic design. And this option sounds very convenient, but it's never worked perfectly because this software auto design, the auto design function is not smart enough and usually generate unnecessary change of flange size and web size. So this option, although it sounds pretty good, but in the real world, we don't use this option because this auto design result is not the ideal design. So instead, we'll use the rating option because the rating option and is pretty neat. And you start with some preliminary design girder size, and based on span to depth ratio and based on some geometric requirement, and you start with a girder size and let the program to do the rating. And based on the rating number, if less than 1, which is good, but significant less than 1 means you over-designed, and you can adjust the size of web and adjust the size of flange in order to make your design more economical. If the rating number greater than 1 means that the strength failed and you need to increase the size of the web or size of the flange based on if shear fails or moment fails. You can adjust the corresponding member size in order to make the girder design work. So the rating is actually more convenient. You just start with some preliminary size, and then based on the rating number, and you can make adjustment and in order to make your design more economical and reasonable. Okay, and line rating is just for one girder lines. If you just want to do one particular girder rating and use that, and one girder line design is just a design of one particular design, and you input the load and let the program to choose the flange and web size. And usually we don't use this option. Okay, so most of the time if we design a new bridge, we'll use this girder system rating, and you have a preliminary size of the girder already, and we'll start from there. Okay, just go to next. And project description, I will put 100-foot simple span. I-plate girder bridge. And unit English, and go to next. And we use load and resistance factor design. It's called LRFD design. And type of the girders, plate girder. Okay, so we use plate girder option. Okay, so after that, generate the file. Okay, generate the file, and I put save the project. Okay. And then we go to the next tab. It's called mode. And now you find the layout mode is active. Okay, so you see the layout mode is active. And then make sure this layout mode is active and go to define. Okay, go to define. And go to define, and only the layout is active. So now you click this layout. And after you click layout, this window pop up and girder geometry. And our girder is parallel, concentric. Okay, so this is the outer girder lines are parallel. And we choose that option and go to next. Number of girders, we have 10 girder lines. And we have same spacing between our girders. So all the girder lines have the same spacing of 9 foot. Girder spacing 9 foot. And number span is only 1. This is simple span. Okay. And span length is 120 foot. Okay. And skew angle, there's no skew angle for this bridge, and the bridge is orthogonal. So we have the 90 degree. The 90 degree means the support abutment is 90 degree to the traffic direction. Okay. And the intermediate braces locations, and we will choose this collinear and radial option. Okay, the collinear radial option, and go to next. And number intermediate braces along girder 1 is 5. Okay, so I explained the 5 intermediate braces at 20 feet, 40 feet, 60 feet, 80 feet, 100 and 100 feet. Okay, 5 intermediate braces or intermediate cross frame. So we have the left bearing to brace 1 as 20, and brace 1 to brace 2, so cross frame 1 to cross frame 2 is 20. So each spacing is 20. Go to next. Okay, radius of curvatures along girder 1. This is the straight bridge, so no curvatures, just none. And concrete strength for the deck is 4.5. Concrete unit weight, I put 150, and this is for the dead load calculation. And overhang width, girder 1, 3 feet. Girder 10 is 3 feet. Depth, slab thickness is uniform. And slab structural and integral wiring thickness, for this one, we put 8 inches. And slab integral wiring thickness portion, so this also called sacrificial thickness. For this bridge, there's no sacrificial, and the wiring surface is provided by the HBP overlay, so we put 0 here. Okay, go to next. And after you define the layout, and after this define this layout, and you can go to generate. Okay, so go to generate and generate girder system layout. Use this option. Okay, so after you generate girder layout, and you can see the framing of the girders and like girder spacing and cross frame location. Okay, based on that. Okay. So after that, after you generate this layout, system layout, now if you go back to the mode, okay, go back to the mode, and you notice that the rating mode become active. Okay, after you generate the girder system layout, and this rating mode become active, so click this rating mode. And after that, you go back to define, and now you find that more of those options become active. So we need to do each one. We need to finish slab, girder, bracing, and loading in order to generate the analysis and rating. Okay, so now you cannot generate rating because all of those options are inactive. So now go back. After you choose the rating mode, now you need to do more input. We already did this layout. Now let's start from slab. And the slab concrete properties 4.5 and unit weight 150. Okay, so good. And then check the slab overhang was 3.3 on both sides. Slab thickness 8 inches and no integral wearing thickness. Okay, and effective slab width, and we have this effective slab width based on the tributary width and varied by interior exterior girder. And take a look at this tributary width for exterior is 90 inches and interior is 108, and 108 is actually 9 feet, which is girder spacing. Okay. And slab haunch, and we have this defined slab haunch and set width to top flange width, and specify the thickness not including top flange, and uniform for all girders, and uniform slab haunch, and here we just put 1 inch minimum. Okay, so which 1 inch minimum, and this used to calculate the moment inertia. Okay, so we do not specify the deck reinforcement, so we just do not do this part and do accept. Okay, so then we're done with the defined slab, and then after you define the slab, you see the check mark. Okay, check mark. Then we'll go to the next, which is the girders. And for the girders, and we define all the girders. Okay, choose define all the girders. So we have 10 girder lines. And types of girder, plate girder, and web splice locations, and the same web splice location for all girders. So for all of those 10 girders, we have the exactly same location for splices. Okay? So same web splice location for all girders, and number of web splice for each girder is 2. Okay? And left bearing to splice 1 is 25, and splice 1 to splice 2 is 70. And the bolted web splice definition, we do not define the bolted splices. Okay, so if you need to design the bolted splice, and we will do it separately, not doing the splice design in this MDX software. And go to next. And girder steel, we use uniform steel for all girders, and specify the girder steel by grade. Use that option, and then go down, choose the girder steel that we use is M270 grade 50 steel, this option, and go to next. And uniform web depths for all girders. Yes, that we use the same design for the web. And uniform depths for all girders, we start with 50 inches. Okay, start with 50 inches, and this is based on the depth to span ratio requirement. And web thickness, we use uniform web thickness for all girders. And uniform web thickness is 0.5. Start with ½ inch thickness. And for flange splice locations, we use same flange splice location for all girders. And top flange splices, we have 2 splice locations. And location is 25 feet, and splice 1 to splice 2 is 70 feet. And number of bottom flange splice for each girders, also 2 locations. And the left bearing to splice 1 is 25 feet, and splice 1 to splice 2 is 70 feet. Okay. And top flange width, we use uniform top flange width for all girders. So usually for design of I-plate girder, we keep the width, the flange width uniform, and change the thickness at splice location. Okay, so I use uniform top flange width. And the starting point, I try 12 inches for the top flange width. And top flange thickness, I will use, since I will change the thickness at splice location, so that option is top flange thickness varies along girder or by girder. So we have the thickness varies along the girder. So it's for the entire girder line, we have 2 splice locations, and we will change the thickness at splice locations. We will make the middle portion thicker than the side portions. So in order to make your design more economical, okay. So choose this top flange thickness varies along the girder or by girder. Next. And so non-uniform top flange thickness, we will choose the same flange thickness by top flange sections for all girders. So usually for design, each of the girder line, we have 10 girder lines, and each girder lines, we have the exactly same design. And so that's actually facilitate the construction in the field, and we don't mess up the interior and exterior girder, and we all have this exactly same design. Okay, and we have 3 sections, and first section is the left side, which is I try 1 inch at the side, and the middle part I try 1.5 inch, and the right side 1 inch. Okay, for the top flange, usually the minimum thickness we start with 1 inch. Okay, then we go to the bottom flange. The bottom flange width, again, I will use the uniform bottom flange width and then change the thickness of each portion. So the uniform bottom flange width for all girders, go to next. And the uniform bottom flange width, I start with 14 inches. And usually the bottom flange is bigger than the top flange. Okay. And then the bottom flange thickness, I will choose. Since I will change the thickness along the girder, I will choose the bottom flange thickness varies along the girder or by girder. And then non-uniform bottom flange thickness, we will choose the same flange thickness by bottom flange section for all girders. So for each girder line, we have the exactly same design. And section 1, I will start with 1.5 on the side, and the middle portion, I start with 2 inches, and the right side is 1.5 inch. Go to the next, and the bearing stiffeners, and we'll use the same number of stiffeners per support for all girders. So have the same, all girders have the exactly same stiffener design. And we'll use 2 stiffeners, and usually we do the 2 stiffeners each side, okay? On each 2 stiffeners above each abutment. Same spacing between multiple bearing stiffeners for all girders. okay? And this 6 inches usually is the standard. We don't change that. And 2 stiffeners at the bearing and space at 6 inches. And usually we use this location for transport the steel girder and do the erection during construction. And bearing stiffener vest, uniform bearing stiffener vest for our girders. And we use 7.5, okay? And bearing stiffener thickness, we use uniform bearing stiffener thickness for all girders, which is 1.5, 1.5 inch thick. Okay. The bearing stiffener size is 7.5 times 1.5. And bearing stiffener corner clip, same horizontal length corner clip for all girders. We just choose that, and 1 inch, and this is standard. We don't change that number. And stiffener steel, uniform stiffener steel for all girders, and usually we use exactly same type of steel as the girder, and specify stiffener steel by grade. Okay, so again, I will choose the M270 50 steel. And intermediate transverse web stiffeners. We do have the intermediate transverse web stiffeners, and that's used as a gusset plate to connect the cross frame to the girder. So we use the intermediate transverse web stiffeners as a gusset plate to connect the cross frame, the intermediate cross frame, to the girder line. So we have the intermediate transverse web stiffeners. And the intermediate transverse web stiffeners for girder 1. Since girder 1 is an exterior girder, so the stiffener only at the inside, at the inside of the web. Okay, so in order to connect the cross frame, we only connect the interior girders. So for the exterior girders, we only have one side of the intermediate transverse web stiffener, which is on the side of interior girder side. So we have one side of the web for the girder 1. Okay? And next one for girder 2, we have 2 sides, both sides, because both sides we need that gusset plate to connect the cross frame. Girder 3, 2 sides, 4 sides, 2 sides. So all the interior girders are 2 sides. Just keep doing that, 2 sides, both sides. Then girder 10 is only one side because girder 10 is also an exterior girder. Okay. And number of intermediate transverse web stiffener location along girder 1, that's 5. Okay, that's exactly same location as a cross frame. And be careful that for intermediate transverse stiffener location for girder 1, and this have you the bearing to location 1, 1 to location 1 to location 2, and this unit is inches. It's not feet. And we know that we provide this transverse stiffener the same spacing as cross frame, and the cross frame spacing is 20 feet. And now we need to change that to inches. So 20 feet changed to 240 inches. So everything is 240 inches. 240. Okay, go to the next. And number of intermediate transverse web stiffener location along girder 2 is 5. And just repeat this. The location is 20 feet. Change that to 240 inches. Same thing for girder 3. So 5 locations for web stiffener and 240, 240, 240, and 240. So all those spacing is 20 feet, which equals to 240 inches. And just keep doing that for all 10 girders, okay? Girder 6, also 5 locations. Okay, 7, 5 locations, 240 is for the stiffener spacing. So the stiffener spacing input is just a repeat work. It's a little bit tedious. Okay, since we have 10 girders and we need to repeat 10 times. Now let this last one, girder 10. Okay, so now we have this intermediate transfer stiffener width. Okay, it's uniform stiffener width. Same for all girders. We all use 7.5 by 1/2. So the width is 7.5. And thickness, we use the same for all girders thickness and 0.5. So that's the intermediate stiffener, 7.5 by 1/2 inch thick. And type of connection plates for our girders, and we will choose this. And this stiffener will be along the entire depth of the web, so it will connect it to the tension flange. Connected to tension flange. Tension is the bottom flange, So this definitely connect to the tension flange because this stiffener will be along the entire depth of the web. Okay, so just do that. Connect to tension flange, and the gap between the stiffener and tension flange, 0. There's no gap. Okay, and we do not provide any longitudinal web stiffeners. So now the modern bridge have no longitudinal web stiffeners, but some very old steel girder bridge have this longitudinal web stiffeners, and longitudinal web stiffeners is not easy to not easy for construction. So now for modern bridge, we already eliminate the longitudinal web stiffeners for I-plate girder bridge. So just select no longitudinal web stiffeners. Okay, so now we define the girders already. Okay, so after you define the girders, you see this check mark, which the check mark. So we're done with the girders. Then next one, which is active, is the bracing. So click bracing, and first we select the bracing steel and A36 steel. So as I said, for the cross frame, for bracing, also called cross frame, we usually use the angle or channel as those members, and those size, the standard steel is ASTM A36 steel. So we choose the A36 and then go to next. And the number of bracing groups, in order to be simple, we just do one bracing groups. Okay, so means that all the cross frame will be the same type, same type, same configurations. And for the bracing definition, and we will choose this specified bracing by type. And the most commonly used is this type B, which is top and bottom chord and diagonal to the center top, and just like a truss. Okay, so I have top bottom chord and two diagonals, and these two diagonals meet to the center of top. It's also called K bracing or Sharon's bracing. I choose type B for our example. Okay, and I just use, in order to be simple, I just use all members same shape. And I use angle. Okay, so this is the most commonly used member shape. Do angle, and I will choose 6 by 6 by my half as a start. Okay, as a start. Again, angle usually is the least expensive piece. Okay, least expensive piece. Usually, you know that if you over design a little bit, it's not a big deal. Okay, so just I choose L 6 by 6 by half. Okay, because this number, based on the bridge spacing, is pretty safe. I just choose that. Head of bracing for group 1, and this bracing usually connected to the transverse stiffener. Okay, transverse stiffeners connect to the web, and the web is 50 inches, and we need to leave like 2 inches gap. Okay, 2 inches gap between the top chord to the flange, to the bottom of top flange of the girder, and also leave 2 inches gap between the bottom chord to the top of bottom flange. So I will put 46 inches because I use 50 inches minus 2 inches on top, minus 2 inches on the bottom, so get 46. Okay. And go to next. And bracing connection distance from the girder web to group 1. So from centerline girder web to the connection, to the bolted connection or welded connection of that top chord or bottom chord of the frame, I will put this, I will use 3.5. Okay. For that, so to 3.5. Say that if you have a 7.5 stiffener, and it's pretty safe, just use half of 7.5. Okay, place like half of the width of 7.5. So we use 7.5 divided by 2. So 3.75 is easy. Okay, so I just put 3.75. Okay, which is half of the stiffener width. Okay, and then after we put this bracing, okay, so now the loading part become active. Okay, so now you still cannot generate analysis rating because this is all gray color, means this is not active, and you need to define all before you can generate rating. So for this define, the last piece will be loading. Okay, so I click loading. And for loading, we will do the non-composite dead load, apply self-weight option. So this is based on the input. Will automatically calculate self-weight of the slab and self-weight of the girder. Okay, so just go that. And then steel weight in addition to the web, flange and bracing members, and specify uniform load by girder. Okay, so I will choose uniform girder. And then in this tab, I actually input I will input the steel deck form weight, steel deck form weight, and for example, so let's go back to this problem, and I put the load calculation. Now we have the steel deck form for interior girder is 0.072 kg per linear foot, and for interior and exterior is 0.036. Okay, so I input this into the software. Okay, so just put right here, girder 1.036 and girder 2 is 0.072. Okay, 0.036 for the exterior girder, and go to next. And tributary slab width for self-weight of girder 1. Okay, uniform tributary slab width. Okay, so girder 1 just based on the half of the girder spacing plus overhang. Girder 2. Okay, so girder 3, this doesn't change. It's just automatically calculated tributary width. 5, 6, 7. All the interior girder is 108, which is the 9-foot girder spacing. Okay, and then concrete weight in addition to tributary slab width times thickness plus hunch, and I put specify uniform load by girder, and this I will put additional hunch weight on each girder line. Okay, so in order to do that, so I'll put the hunch weight. Okay, so put 3 inches hunch and 0.150 kg per cubic foot times 3 inches times 12 inches, which is top flange width, divided by 144. Okay, so I get 0.0375 kg per linear foot. Okay. $375. That's the hunch. Okay, that's the hunch on each girder line. Okay. Go to next. And non-composite dead load, no concentrate load. Okay, so we just did the uniform load. And then composite dead load only specify distribute load. And distribute load, composite dead load, is specified uniform load by Girder. Okay, by Girder. Okay. And for Girder 1, this is the composite load including, for this one, including the median and the concrete barrier. So let's take a look at the load. And we have a composite DC and a median and a concrete barrier. So we have a total, okay? So based on the median and concrete barrier, and we have the total is 0.45 plus 0.9 divided by 10 girder lines, and we get 0.135 cube per linear foot. Okay, 0.135. That's for the composite dead load, including the median and the barrier on each girder line. Okay, so go to the next. And a varying surface load applied uniformly to all girders. Okay, so we'll use that because it's composite load applied uniformly to all girders. And go to next. And this number is based on our calculation of the load. We have a DW and deck overlay 36 and utilities 5. So we get 41 pound per square foot total DW and get 0.041 kg per square foot. Then we use 0.041 kg per square foot times the total width of the bridge, which is 87. Okay, and this is the area load times the width, we get kg per linear foot. And then divide by 10 girder lines, get 0.3567 kg per linear foot on each girder. Okay, so we need input this number into the program. So 0.3567, okay, per girder. And truck definition, we have the HL93 design truck, tandem, and permit truck. Okay, so we have HL93 as well as the New York DOT permit vehicle. And the tandem truck, we use HL93 tandem truck. And then the permit truck, we have New York DOT permit truck 11 axles. And axle spacing, axle load, we have 10. Okay, so just refresh your memory for the New York DOT permit vehicle. Okay, so we have 11 axles, then we have the axle load, okay. And then we have the axle spacing, okay. So we need to input that into the program. Okay. So we have a 10, 18, 18, 23, 23, 23. Then we have 5 21s. Okay, so just 21, 21, 21. Okay, so then we have the 11 axle load and go to next. And the spacing 1 to 2 is 9 foot. Then we have 4 spaces of 4. Then 10 feet. Then we have 4 spaces of 4. 4, 4, 4, 4. Okay. So get axle spacing for New York DOT permit vehicle. Then we have axle, the wheel spacing is 6 foot. And define lanes, we have 7 lanes. Okay, so we use the clear roadway 84 divided by 12. And no unloaded lanes represents median. So we assume that in the future it's possible the median will be removed and widen the bridge. Okay, so we just, for design, we need to consider future widening. So there's no unloaded lanes represents median. And go to next. The lane width 12, 12, 12, that's good. And uniform roadway width. Okay, roadway definition, and roadway width perpendicular to the girders is 84. Okay, that's the clear roadway width. And right curb distance from girder 1, the right curb distance, this is from the inside face of the curb to the center line of girder 1. So we have the overhang, which is 3 minus 1.5, so we get 1.5 feet. So this is uniform distance. Okay, so this is the, because it's all those girder lines parallel, have the same distance. And the right curb distance from girder 1 is 1.5 feet, but it said outside girder is negative and inside girder is positive. So this right curve, the inside curve is outside, the outside girder 1. So we have negative 1.5 represents outside the girder. The curve inside face is outside the girder line. Okay, negative 1.5. And we use float lanes between curbs. Okay, and no sidewalk. Okay, so now we define the girders and the loadings. Also, we finished the loadings as well. So everything in define already been finished. So now I want to save the project. Okay, save the project. Then if you go after you finish all those define, finish loading, and you see the generate analysis rating is become active. So now you just click this analysis rating option. Okay, so when it's ready, it's already the complete the analysis rating. And what we will do is we would like to take a look at each girder line. So I will do the girder one. So I will check each girder one. And for girder one, I want to take a look at the rating output. Okay, so the rating output to make sure my design is good. And for rating output, I will do that there's a lot of options that you can see, okay. And like bearing stiffeners, the ratio is 0.115, which means that it's really safe for bearing stiffeners. Although that this ratio is pretty low, but we still use the 7.5 by 1.5 inch because those design standard and those stiffeners and used in the erection of the steel girder, and this is important to make sure that the bearing stiffener is safe. Okay, and for the rating output, the most important thing for the bridge design, girder design, is the maximum performance ratio. This one, okay, this maximum performance ratio right here. And for based on the maximum performance ratio and just currently it's girder 1, the exterior girder, and we want to take a look at the ratio, and this one to give you the maximum performance ratio. And you can see that for shear bending, and they have the design tandem track, this HL93, and it makes this the first line is if you use HL93 and you have the shear performance ratio is 0.9, and we target that maximum performance ratio is definitely need to lower than 1, and greater than 1 represents a failure, and smaller than 1 means it's meet the strength limit. And also we want the this performance ratio not significantly lower than 1, like 0.3, 0.4, things like that. And 0.5 means that your design is too conservative, and we want to target the maximum performance ratio is ranging from like 0.6 to 0.99, and that range is the best. I would say that like the best design is around like 0.7 to 0.9, that range is the most reasonable design performance ratio, 0.7 to 0.9. So based on that, let's take a look at our design. And for girder 1, shear is 0.917, and this is pretty good, okay. And the bending, the maximum ratio is 0.881. And for the permit vehicle, girder 1, the shear is 0.917, and the bending is 0.860. So means that this girder design is for shear bending both look pretty good. And this, since it's a bridge, is steel bridge, we also check fatigue. As a fatigue check, this also pretty good. Okay, so the fatigue check, we usually target the strength, shear, and bending, and those 4 numbers. Make sure those are in a reasonable range, like 0.7 to 0.9. And for girder 1, this pretty good. Let's take a look at girder 2 maximum performance ratio. And for girder 2, we have the shear maximum is 0.905, and the bending is 0.840. Okay, and for permit vehicle, the bending shear is 0.823, and bending is 0.698. Okay, and just to check the remaining girders. Okay, girder 3, 4, 5, 6, 7, 8, and 9, 10. Okay, so we find that so those maximum performance ratio is in the 0.8 to 0.9 range for the HL93 live load and permit vehicle, means that our design is pretty reasonable. And so if you want to take a look at the detailed, okay, to detail the rating, you can go to the bottom flange. Okay, so bottom flange and give you the ratio at each at 10th point. Okay, so for this ratio, it's at 10th point, and you can see the design. The last column, the ratio at each point, and we can see that the design, if if you want to adjust your design, you can refer to this ratio. If the ratio is pretty low at some spot, the governing, because for middle one, the governing is 0.86, and for the first segment for splice, the maximum is 0.702. Okay, so means that those designs are pretty reasonable for bottom flange. We don't need to change anything. And take a look at the top flange. Top flange bending stresses, and for stress 1 and 2 loading, and let's take a look at that. And the ratio. Okay, so this gives you the ratio for top flange. It seems that for our top flange, our top flange design is more conservative because the maximum ratio is around like 0.72. Okay, so let's see the 0.72. The top flange maximum ratio is like 0.7. This one is close to 0.75. Okay, so means that our design is pretty reasonable because top flange we already use the minimum 1 inch thickness. So there's not large room for us to adjust our design. So means that our design is pretty good. It's not over conservative, and those ratio is in a reasonable range, like 0.7 to 0.9 range. And we can say that our design is pretty good. We don't need to change anything for this design size. And after that, we also need to check the deflection. Remember, the maximum level of deflection is 1.8 inch. So we need to take a look at the deflection. And for Girder 1, and we have the live load deflection, the maximum Girder 1 is 1.571, okay? So less than 1.8, which is good. And take a look at interior girder, and interior girder is maximum is 1.298. That's good. Okay, so girder 3 is 1.19. Girder 6 is 4. Okay, check every girder, make sure it doesn't exceed 1.8. Okay, so it seems that for this bridge, exterior girder governs. Okay, this is the 1.19 maximum level of deflection, and 9 is 1.298, and 10 is 1.571. Okay, so all less than 1.8 means that the service limit is good, and we don't need to change the depth of the girder. And now we find the strength good and service good, and so this design is sound. Okay, so I think means that our design is good. If you just go to the girder system and you can find the deflection summary, okay, deflection summary, and we also can find the input file. Okay, So this, based on the output, we can find different things based on the Girder line. Okay, so if you want to take a look at other information like, reactions and the shear strength as splices, and just give you a lot of results. Okay, but for Girder design, we focus on the maximum performance ratio as well as the deflections, so we can check both strength limit as well as service limit. Okay, so that's it for this example. Okay.